Okay, so I want to evaluate the integral from minus infinity to positive infinity of 1 over x squared plus 1 to the third power, okay? So the first thing I will do, as usual, is find the poles. Okay, so I want to use the residue theorem to evaluate this integral. The first thing I want to do is find the poles. So I will set the denominator equal to 0, so x squared plus 1 equal to 0. Okay, that it's to the third power in the denominator. It doesn't change anything. We could do it here also, and then we could take the third square root. But here we have 0, so the third square root of 0 is still 0. Okay, so it doesn't change anything. So we would be left with x squared plus 1 is equal to 0. And then we find out that x is equal to plus or minus I. So that are our poles, plus and minus I. So now we have a pole of order n is equal to 3, okay, because everything in the denominator is to the third power. So we need to use the formula for poles of order n greater than 1, okay. 1 would be easier, but here we have no luck. So n is equal to 3, so we use the general formula. So we have 1 over n minus 1 factorials times the limit as x approaches our poles times the nth minus 1 derivative times x minus our poles to the nth power times our function f of x, okay? So in this case it's 1 over 3 minus 1 factorials times the limit as x approaches our poles at plus or minus I times the third minus 1 derivative, so the second derivative, times x minus plus or minus I to the third power, okay, because n is equal to 3, times our function, so 1 over x squared plus 1 to the third power, okay. Yes, and so we will use it, but first we need to make a choice. We need to choose which contour integral we will use, so the upper half circle or the lower half circle. So if you go counterclockwise, in the upper half plane through along the upper half circle with radius infinity, or clockwise along the lower half circle with radius infinity, okay. So here the radius, this thing is always, the radius tends always toward infinity, as we will see later, okay. Yeah, so anyway, so it doesn't really matter here because we don't have an exponent in our nominator. By that I mean we don't have something like e to the ix or e to the minus I omega x. So that thing generally we have it if we make a Fourier transform, and that thing we have it generally if we evaluate the integral with something like cosine of x or sine of x in the denominator, okay. So if you have something like the integral cosine of x over something blah 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 dx from minus to positive infinity or 0 to infinity, whatever, okay. But here, and then we say that this cosine of x or sine of x is the real or imaginary part of this e to the ix, like that the integral with cosine of x blah 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 is the real part of the same integral with e to the ix blah blah blah, and with sine the sine of x is over blah 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 is the imaginary part of the same thing with e to the ix, okay. But here that's not the case. We only have one in the above the fraction bar, so we don't care. So we can basically choose our contour, okay. We don't fear that there will be an we don't need to find an exponential decay, so something like e to the minus infinity. So we also don't fear that we will get something like e to the infinity above the fraction bar, okay. So we don't fear it, so we are free to choose. We just need to make sure that if we take the first contour, so counterclockwise in the upper half plane, we will multiply the residues using the residue theorem with 2 pi I, so positive, okay. If we go in the lower half plane, so clockwise, we will need to multiply the residues with minus 2 pi I, okay. Because in math, remember, if something is counterclockwise, it's positive. If it's clockwise, it's negative. That's the only difference. And of course, the poles will be different. If you go in the upper half plane, our pole will be only I, okay? there will be an I somewhere here, because negative I would be outside the region. But if we go in the lower half plane, we only have negative I somewhere here, and positive I would be somewhere around here, so outside it, so we won't care about it. Let's choose for fun the part in the lower half plane, just that we need to multiply with negative 2 pi I. It's maybe a bit small, little bit harder, I don't know. So let's choose this part. So here we can compute our residue. So we have the same formula as here, but now it's the limit as x approaches negative I, because I said positive I is not in our domain here. Okay, it would be here inside, but not here. So we have the same thing as here above. So we have 1 over 2. So okay, so 1 over 2 factorial. Sorry, doesn't change anything. It is 1 over 3 minus 1 factorial. So it's the same thing here. Times the limit as x approaches negative I. Times the second derivative, okay, 3 minus 1. The second derivative of x minus I to the third power, okay, so again, positive I is not inside our domain, so we don't care, we only have negative I, times our function that was factorized, okay, instead of writing x squared plus 1 to the third power, we can factorize it and write x minus I to the third power times x minus I to the third power, okay. Let's just refactorize it because we found the poles. So now this part here, this minus I and this minus I here, they cancel each other out, and we're left with the second derivative of 1 over x minus I to the third power times 1 over 2, okay? Times the limit as x approaches negative I. So we can take the second derivative of that x minus I to the third power in the denominator. And remember that thing, it's easy to take the derivative because we can write it as x minus I to the negative third power, okay? And so we can use how do you name that, the power rule, whatever, the exponent comes above and we make minus 1. And then we do it a second time and we're done, okay? So we get, after derivating, 12 over x to the minus I to the fifth power, okay? Times 1 over 2 again, times the limit as x approaches negative I, and so we get 3I over 16 as our residue, as our only residue, okay, 3I over 16. So now again we use the residue theorem. We know that our contour integral is equal to minus 2 pi I, because we are in a clockwise direction, as said, times the sum of the residues that are inside our domain. So I said we only have one residue, is 3I over 16, okay? So again, we will notice, as in the last videos, that our contour integral along the real axis, so from minus infinity to positive infinity, okay, so here, so this one here, that will simply be our original integral, because if we can use dummy variable. I didn't show it in the last videos, but here I can just show it. If we let x be equal to t, so t is a dummy variable, dx is equal to dt, and t is between minus infinity and positive infinity. Now we replace every x with t, and we see that it's exactly the same thing with simply with t, okay? We would have the integral from minus infinity to positive infinity, minus infinity to positive infinity of 1 dt, 1 dt over t squared plus 1 to the third power. So that is simply our original integral, okay? So our original integral can be called I, okay? That is defined as I, okay? So now we will prove that our second part vanishes, because again, as usual, we want to prove that this second part here vanishes as our radius r gets larger and larger, like here. Okay, when the radius tends toward infinity, we want to show that the second part here, so the part around this semicircular axis vanishes, and so we're only left with our first part along the real axis, which is our original integral, and you can set that equal to minus 2 pi I times the sum of the residues, and we're done. That's generally what we do in with the contour integrations and the residue theorem. Okay, yes. So let's prove that the second part along this semicircular axis vanishes. So let x be equal to r e to the pi I t. Okay, so r is our radius, as said, because it's e to the pi I t is a circle, okay, with radius r. t is between 0 and -1. Why? Because this e to the pi I t is a circle, I said, okay? If t is between 0 and 2 or 0 and -2, we do an entire circle, okay? Like this or like this, okay? Here, if we go like this, t is between 0 and 2, and if we go like this, t is between 0 and -2, okay? But if t is simply between 0 and 1, we get something like that, so half a circle, and if t is between 0 and -1, we get something like that, and that is our path, our semicircular path in the lower half plane, okay? And our dx will be equal to pi I r e to the pi I t dt, okay? There should be a dt here, sorry. So we just take the derivative of this r times e to the pi I t with respect to t, okay? So now we replace everything, every x and dx with t and dt. Also the integral boundaries, they change, as I said, because now we are not from minus infinity to positive infinity, but from 0 to -1, okay? So 0 and -1. We have our dx here, because here we have 1, so we don't care. We have our dx here, which is now pi I r e to the pi I t dt. And in the denominator, instead of x, we have r squared e to the 2 pi I t, okay? Because x is, as said, r e to the pi I t, which is a circle of radius r, as said, and r will tend toward infinity, the radius, plus 1 to the third power, okay? So it didn't really change. We did not change anything, really, okay? Sorry, no, we just replaced everything with t and dt. Yeah. So now we can see that this integral is roughly equal to r to the r over 6 power, okay, because we have an r here, and here we have an r squared, but if it's everything to the third power in the denominator, so we would be left with r over r to the 6th power, okay? And so that is equal to 1 over r to the 5th power, which will tend towards 0 if r tends towards infinity, okay? Yes, okay, so I hope this is clear. Okay, the radius gets larger and larger, and so we would be left with 1 over r to the 5th power, and so that would be something like 1 over infinity to the 5th power, and that tends towards 0, okay, because it is really, really big, okay. So our second part vanishes now. Okay, we can clear it out, it's 0 basically. And so I said our first part along the real axis, okay, so this part here vanishes, but this part is our original integral along the real axis. So that would be our original integral, I plus, so big I for integral, I mean, okay, that stands for integral, holy shit, why? Integral, okay, integral, it should be written. So our original integral plus 0 is equal to minus 2 pi I times the sum of the residues. Again, minus because we are clockwise, okay? It's it's like, we go like that. Here, in this case, it would be counterclockwise, it would be positive. That's why we only do 2 pi I here, but we have chosen this counter here, okay? Yes, and again, here we don't care about which counter we take because there is no exponent. We don't have e to the ix or e to the negative I omega x, something like that. So we are free to choose our counter, okay? But if we add an exponent, or as I said, the real or imaginary part of e to the ix, okay, with something like cosine x or whatever, we would be forced to choose one of both paths, okay? But here it's not the case. So we are free to choose, okay. So minus 2 pi I times the sum of the residues, so our only residue inside is this one here, I said, so 3i over 16. So we multiply that out, and we get 3 pi over 8, okay, and that's our final result, 3 pi over 8. You can check in Wolfram alpha, it should be correct, okay. So as usual, find the poles. Pole of order n is equal to 3, so greater than 1, so we need to use this big formula here. Instead of simply the formula with h of x over g prime of x, sorry, you can't read, h of x over g prime of x, it would be if we have a pole of order 1, so n is equal to 1, but that's not the case here, sadly. So then we calculate the residues. We are free to choose a path, of course, and then the residues will depend on the the poles that are inside our domain. Okay, so as said, then yeah, we proved that the part along this circular axis, be it here, this case, or if you had chosen the other way, like in this case, we proved that this second part too vanishes as our radius gets larger and larger. So we let x be equal to r e to the pi t, and so on. And then we notice that we have something like e to the r over 5. And so if the radius r gets larger and larger toward infinity, we will get 0, okay? And so we're left with the original integral, so along the real axis of the part number 1, which is equal, according to the residue theorem, to minus 2 pi I, or positive 2 pi I times the sum of the residues, okay? And that's it, okay? And yeah, I think that's it. So we proceed as usual, and we're done, okay? So yeah, thanks for watching. I hope it was clear.